Okay, tonight's presentation comes from Dr. Charles Merguerian, an active published research scientist in the fields of geology and astrogeology and professor of many lunar geology courses. Charles Merguerian is internationally recognized as the leading authority on the geologic structure and tectonics of New York City. He is the principal principal of Duke Geological Laboratory in Stone Ridge, New York, professor emeritus and former chairman of geology at Hofstra University, 1981-2013. And he's a curatorial associate at Yale University and has a broad range of expert consulting experience. Tonight's title of Dr. Merguerian's talk is Exploration and Geology of the Earth's Moon. With that, let's give a warm welcome.
All right, well, thanks very much for the nice introduction. It was the second nicest introduction I ever had. The best one was when the guy didn't show up and I got to introduce myself. It's a pleasure to be here tonight. I haven't spoken about lunar geology in quite a while. So I spent a couple of days actually catching up on what I've missed the last 10 years or so. And in fact, this video is the last mission that landed on the moon. It just happened a few months ago in March of this year. This is the Blue Ghost Firefly Aeronautics mission to land on the lunar surface. So we're still active, but of course the heyday of Apollo and lunar exploration ended in the 70s. It's hard to believe, but it's been 50 years since we've had anybody on the lunar surface. That's going to change with the Artemis mission coming up in, I think next year, there's going to be some progress on the Artemis. But this is a nice view of the landing site of the Blue Ghost. And you can get these online pretty easily, actually. Okay. Jules Verne is the place to start here, because Verne, in 1865, wrote the famous book From the Earth to the Moon. It was made into a movie in 1958. And he envisioned a coal-powered rocket to the Earth's moon and correctly foresaw the military impetus for space travel. In addition, he predicted the area near Cape Canaveral, Florida for US space missions, recognizing that it was the southernmost point of the United States that therefore had the greatest linear velocity and was an assist to launching space vehicles. Jules Verne was very instrumental and was a wonderful inspiration to many of the scientists, and I'll explain some of that. So the basic outline of tonight's discussion, and I have way too many slides, I'll try and get through them. I'm going to talk a little bit about the exploration of the moon first, because it's an interesting story. And this whole presentation is the result of not having a cell phone as a kid, because all we had was watching rocket launches on crappy old black and white TV, you know. Boy, we didn't miss too many of them. It was a very exciting time. One of the first movies was the movie, let me go back, Trip to the Moon, by George Méliès, who made about 300 movies or something like that in the late 1800s to the early 1900s. And in this movie, he actually has space aliens. I just saw a shot of one next to the rocket. It's an interesting movie, silent movie, obviously. and it depicts space travel. They digitally re-enhanced this thing and colorized it so people can actually get this. And of course, the internet is wonderful. So you had a wonderful launch team there. You can see. Anyway, it's an interesting movie, just in terms of really the first movie to highlight space travel. Many books were written about it before then, but this was the first real moving picture to highlight space travel. And Miele was the first one to use stop motion photography for movies. In 1929, a 95-minute silent movie, The Woman in the Moon, also highlighted space travel. Herman Oberth, who we'll talk about later, one of the early rocket scientists, a Romanian fellow from Transylvania, in fact, he built a rocket for the opening of this movie. It's a Fritz Lang film made by UFA Studios and German movie. And this rocket was actually built as a promotional gateway for the movie itself. Some of you may be familiar with this movie, Destination Moon, 1950.
It is just 1 minute before takeoff time in the uninhabited desert of White Sands, New Mexico.
Tell them to stand by for counter
Notice
open
no
firing.
spacesuits.
59, 58, 57.
But to reach this dramatic moment were months of construction, checking every detail 1,000 times, and a desperate struggle to convince the skeptical, to outwit those who would stop us, to muster up courage to challenge the black, airless void of terror-stricken space.
Come back to me, Charles. Please, come back.
Come back. Same year, rocket ship XM with Lloyd Bridges. And again, this movie kind of highlighted the idea of getting to the moon. I think in this movie, they wind up going to Mars by mistake or something like that. But, you know, the whole idea was there. And of course, the visuals, right? Jack and I were talking about this on the phone. I've always felt, and in fact, I have a series of lectures on these movies because I always felt that they were a way to get the public to accept what was going on in terms of scientific exploration. Radar Men from the Moon. This is a Republic Pictures serial, over 2 hours long. Again, Commander Cody, the Sky Marshal of the universe, and off to the moon. My personal favorite, Cat Women of the Moon.
Incidentally, where are your menfolk?
You're the first man I've ever seen.
Can you imagine? Put me in, coach, you know. Can we make this a little bit louder somehow? Oh, really? Okay. All right. Fine. Okay. Enough for the fun stuff. Let's get into it. Two of the big names in early rocketry, of course, is Konstantin Tsiolkovsky and Robert Goddard in the United States, Russian and US. Tsiolkovsky was a Russian school teacher, and his first book was called Free Space. He was about 20-something years old when he wrote this. It was a bestseller. And it kind of set the stage for his ideas about space travel, and he proved mathematically that space travel was possible. It was the first attempt at mathematically showing that this could be done. And he talked about the reaction principle in this book, Free Space. In about 12 years later, he published Dreams of the Earth and the Sky. He set plans for a reaction thrust motor, and then 1903, exploration of space with rocket devices. where he proposed that liquid oxygen and liquid hydrogen design and provided all of the basic equations for rocketry. I can't overemphasize the importance of Tsiolkovsky's work in setting us on the right path. Near the end of his life, he got interested in weightlessness and described some of that, and envisioned older here, a passenger rocket train by 2017, 300 feet long and 12 feet wide. He wrote over 60 articles on astronautics, rocketry, and other allied subjects. And in 1935, I think the year of his death, the publication of Na Lune, on the moon, another Russian contribution. Now Goddard, who was kind of a shy, reclusive gentleman, was the father of American rocketry, and he was an independent experimentalist. He's shown there with his successful rocket. He discovered that liquid hydrogen and liquid oxygen served as efficient propulsion. Of course, he's following Tsiolkovsky's lead on that. And he also provided mathematics for the feasibility of rocket, and received a US patent for multi-stage rocketry, and proved that rockets would work in a vacuum. First flight of a liquid fueled rocket in history was in 1926. He came under some scrutiny by some bad press in the New York Times. And rather than promote his own act, he just got reclusive and went out to New Mexico. But this launch was taken at his Aunt Effie's farm in Auburn, Massachusetts. That's the site of the first launch. This is the rocket itself, and Goddard there to the right. The fuel is down at the bottom there, and it's pumped up to the rocket nozzle itself on the top of the structure. And the thing, I think it flew something like 26 feet or something like that. So the first successful rocket launch, also the first scientific payload on a rocket. He put a barometer and camera up there. Guidance system development and guided rocket with a gimbaled motor, where the motor would move in order to change the trajectory of the rocket itself. All of these are Goddard's. By 1931, the rockets became a little bit more sophisticated, larger and larger by 1935. And by now he had really kind of set himself up as the master of American rocketry. At about the same time, rocket societies, civilian rocket societies, were opening through the US, Soviet Union, France, and Britain. This is a picture of the German Society for Space Travel Journal. And these private groups, kind of like yours, were developing scientific experimentation and implementation of rockets. And it was also on four-wheel rockets. This is Max Valier, who in March of 1928 basically created a rocket car using liquid propellant. And he wrote a book called The Advance into Space. Now, similarly, at the same time, the Soviet Union was active. There were rocket societies and people that were interested in this stuff. There was a 9-volume encyclopedia written between 1928 and 1932. So all of this was happening pretty much at the same time on various parts of the globe. Aubert, who read Jules Verne at the age of 11 and was fascinated his entire life with space travel as a result. Aubert is the one that made that rocket for the opening of Frau im Mond. He published Die Rocket zu den Planeten, Rocket into Space, 92 pages. And in 1929, a much expanded version came critical acclaim. And he worked with Dr. Werner von Braun in the 30s, and then at Peenemünde at the north coast of Germany, and then ultimately in the United States in the 1950s and 1960s. He was along with von Braun and Dornberger and a number of other people, Oberth, Nebel. They're the guys that are responsible for the US space program. There's no question about it. Here's a picture, in fact, of von Braun there on the right, Oberth and Nebel, three of the rocket scientists that were responsible for the development of small but effective rockets. Here's another picture of von Braun at 19 years old, again, in the realm of rocketry, right? Now, by 1932, after World War I and the restrictions imposed on the Germans for arms, but what was not covered in those treaties was rocketry. So by 1932, Captain Walter Dornberger witnessed a launch by the von Braun team and Nebel and Oberth. And although the rocket itself didn't impress him, he was impressed with von Braun. And he enlisted von Braun, and most of the German Rocket Society followed von Braun into military service. And there are some controversial discussions, in fact, about von Braun's input into the German war machine. He was more interested in the science. And in fact, von Braun was arrested and jailed by Goebbels because he felt that von Braun was more interested in rocket science and actual military rocket development. So they basically developed weapon systems not covered by the various treaties at the end of World War I. The site for most of the rocket development was Peenemünde on the Baltic coast. It was established in 1936. It's a peninsula that sticks out into the water there. And the launch facility is shown here. The British bombed, during World War II, the British bombed Peenemünde, and the Germans moved their production facilities with extensive use of POWs, by the way, as slaves. They developed underground and tunneled construction at Nordhausen and Mittelwerks to the south and to the west of Peenemünde. In 1944, 1945, near the end of World War II, everyone is aware of the barrage of rockets that were launched and the supply chain. The red line up there is the German front at that time, and the use of rockets to bomb London and also to bomb Antwerp, right in the center of this thing, where the Allied forces were concentrated, was used by the Germans and created a lot of havoc. First the V1 and then the V2 rockets were developed at these sites at Nordhausen and Peenemünde and the Mittelwerks. Now the Russians, Korolev, he was the grand designer for the Soviet rocketry program. He had great vision on Soviet rocketry. He wrote a paper called the Commission, and that paper inspired the creation of the Commission for Interplanetary Travel. And he submitted plans in 1955 for a satellite to the Soviet leadership, which was accepted. His main proponent was Khrushchev. Khrushchev was a big fan of Korolev's, and he depended upon him for the new Cold War kind of approach to being first from the United States. The Allies, with the sound of Russian guns in the distance as they came in from the east towards Peenemünde, the German rocket scientists decided to surrender to the Allies, and the Allies got, I think the technical term is a shitload of German engineered rocketry. They took a lot of the hardware. The Russians got, when the Russians finally got there, they got some as well. But we got the cream of the crop in terms of personnel, and we also got a lot of rocketry that was sent back to the United States and set up in White Sands, and then eventually in Huntsville, Alabama, where the rocketry program of the late 40s and early 50s really blossomed. And it started with a whole series of launches of V2 technology taken from the Germans in that end of war period. The International Geophysical Year is actually a year and a half. It was a global agreement and effort to launch satellites for peaceful scientific purposes, but nobody was fooling anybody. The military impetus for space programs, as originally proposed by Jules Verne, was in full force. And there's no question about it, this was a military race for domination of space. We set up the Army Ballistic Missile Agency, the ABMA, in Huntsville, Alabama. The military was in charge. And you can see from this image, that's Oberth in the front and von Braun and a few other fellows that were involved in the development of rockets for the United States. They had a lot of failures. There's some interesting videos on the types of experimentation that took place. There was one rocket I remember that took off from Alabama and it landed in Texas. And these guys were known as the first German group to attack the United States. With these rockets that were going in all different directions. Some of you may remember all the horrifying mistakes that were made. So who's in charge? By 1955, the US Navy was charged with developing the Vanguard program to launch the first US satellite during the IGY. And the NACA, I always forget what NACA stands for, but it's something civilian authority. That became the National Aeronautics and Space Administration in 1958. And again, under the guise of civilian research, the development of rocketry took place. I was involved in that, by the way, back then. The Sputnik State Commission, Sputnik 1 was launched while we were watching the World Series. The Russians launched Sputnik 1, and it started circling the globe, 185-pound, 23-inch diameter satellite that was beeping. And beeping, there's an article about the New York Times, the United States, complacent, the Russians are sending things into space, and we're not. Purposely, the data, I mean, there was no data, it was just a signal from Sputnik. It was broadcast at the ham radio frequency. So every ham radio operator around the world could hear it and say, hey, look, they've got something in space. We have nothing, right? So things started to heat up, and a month later, they put Laika into space. Space Dog. He didn't do too well. There was no recovery per se, but the satellite weighed 1,100 pounds, and the message was clear. If the Russians can put 1,100 pounds into space, they can put nuclear weapons into space too, because they're heavy. Russians always had the big rockets, much larger than ours. So by 1957, the Soviets had big intercontinental ballistic missiles. The United States had yet to test the much smaller Atlas class. And they launched the space age, there's no question about it. We were behind them for quite a while. In fact, I would say until 1969, we were behind the Russians. And there was a fear that the Russians could develop a first strike capability as a result. Vanguard 1 in December of 57. You may remember this, I remember it. The thing just collapsed on itself. The nose cone broke off feebly as the thing descended into a ball of flames. So that was the Navy Vanguard. And at that point, I think it was NACA at the time, not NASA. They said to the Navy, hey, look, you know, nice try. We're going to go with the Army missile development. And our first satellite was launched in January 58. Now, it always impresses me the rapidity with how things happen. This is a month later, right? In a month, they changed the entire support systems at Cape Canaveral to support a totally different missile system, the Redstone rocket. And this is Redstone rocket. They just took one off the shelf, literally. This was in Huntsville, Alabama. And the number there is UE for 29. If you spell out Huntsville 1 through 9, those are the numbers that they used for the rocket. So this was just an off-the-shelf Redstone rocket, and it was successful to launch using the Jupiter C. And you might remember that top of that thing would start spinning before the launch and take off. It was just an unbelievable development. So we finally made it, right? We put a satellite, and it was actually a very technically astute machine, and actually sent back data, unlike the Sputnik. This is the telemetry from Explorer 1 satellite, and had instruments for cosmic ray, temperature, micro meteorites, low and high power radio transmitters. And this represents our first package. That little thing is the Vanguard. It's that, that's the Vanguard 1. So after the Explorer 1, then the Navy took another shot. There were a couple of other disasters though. And then finally they got Vanguard 1 into space, competing with the Army in this case. At about this same time, NASA was created. So the IGY resulted in about 6 globe encircling satellites. The Sputnik 1, 2, and 3 were close to Earth. We had orbital superiority, for what it's worth, with the Vanguard and Explorer systems. The Russians changed their attention to the moon at this time, and the Luna missions. This program started in 1959. The first one, Luna 1 in January, bypassed the moon by 4,600 miles, so that one missed. But Luna 2 did impact the moon, and Luna 3 actually went into circumlunar orbit. That was October of 1959, and provided, you may remember, the first images of the lunar far side. And there it is, the Luna 3. It looks like a washing machine, you know. But anyway, it did return this image of the lunar far side, a part of the moon that no human had ever seen before. It was another technological dart in the board for the Russians. Yuri Gagarin, you might remember, was the first human to orbit the Earth in April of 1961. So they beat us at that also. The Vostok 1, a massive rocket, shown here, kind of similar to the configuration of the Saturn V. And ironically, in 1968, he died in a plane crash. He was the first guy to circle the Earth. Unbelievable. And then their next flight, there were multiple orbits. Well, the Mercury
Project Mercury, America's first manned space program, lasted from 1958 to 1963. The Mercury 7, test pilots all, Scott Carpenter, Gordon Cooper, John Glenn, Gus Grissom, Wally Schirra, and Alan Shepard Jr. and Deke Slayton. Their task proved that man could fly into orbit around the Earth and return live and well to talk about it. Shepard was first in Freedom 7. His 15-minute suborbital hop on May 5, 1961, proved the United States was catching up with the Soviet Union. 3 weeks later, President Kennedy's call for a lunar landing.
Commit itself to achieving the goal
3 weeks.
before this decade is out of landing a man on the moon and returning him safely to the Earth.
Kennedy upped the ante. He put it on the line. In 1961, he announced that the United States would have a man on the moon by the end of the decade. And the race began. Second human into space, it was a suborbital flight. It's kind of an interesting story. Back in those days, there were tremendous technological difficulties, all kinds of holds, 2-hour holds, 3-hour holds. And I remember distinctly as a kid watching Shepard staring first at the rocket on the ground, getting in the gantry, going up. And in those days, they used to feed them this huge breakfast, steak and eggs and orange juice and coffee and the whole, the whole bit. So Shepard's up on top of the rocket, and there's a hold, 2-hour hold, and there's another hold, and Shepard calls down. He says, "Hey, look, fellas, I don't know how to tell you this, but I got to go to the bathroom." And they said, "Well, whatever you do, don't pee in the spacesuit because there are all these electrical connections, things will short out." He goes, "You don't understand." He goes, "It's more complicated than that." And they said, "Well, please, About 10 minutes later, he calls down and says, "Well," he goes, "it's too late." And at that point, they wanted to scrub the flight. So he's sitting there in a bit of a mess in the spacesuit, and he calls down and he says, "Look," he goes, "light the candle. Let's see what happens." So it was the true grit of Shepard that got us on the board there in terms of suborbital flight. One other interesting story is after the flight, of course, he's in the motorcade with Lyndon Johnson, who was a big proponent of space exploration. And Johnson turns to him and he says, the people lined, cheering, he goes, "You're a famous guy now." He goes, "Let me give you a little tip." He goes, "Let me give you 2 tips. He goes, "Number 1, never pass up a free meal. And number 2, never pass up the opportunity to visit the men's room." This is the rescue of Shepard's suborbital splashdown in May of 1961. Now, Kennedy not only announced it to Congress 3 weeks later, but in the next year, his famous speech.
And they may well ask, why climb the highest mountain? Why 35 years ago fly the Atlantic? Why does Rice play Texas? We choose to go to the moon. We choose to go to the moon. We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard. Because that goal will serve to organize and measure the best of our energies and skills. Because that challenge is one that we're willing to accept, one we are unwilling to postpone, and one we intend to win, and the others too.
So Kennedy puts it on the line with the Russians. And he says, "Look, we're going to beat you to the moon." Of course, he was killed 2 years later. Was it 2 years? No, it was 1 year later, 1963. And almost to support his vision, things got ramped up at Cape Canaveral. Thousands of engineers came to Cape Canaveral, many of them with just bachelor's degrees. And they got the system going, first with Mercury, and then the Gemini missions, and then eventually the Apollo missions, and not without some bumps in the road, as you might remember, for example, Apollo 1. Now, at the same time, Project Ranger started our lunar exploration, and Project Ranger was a pretty basic machine. It just basically crashed into the surface and took as many pictures as it could. And we started analyzing those pictures and started developing different spacecraft to do different things on the moon. The Lunar Surveyor program, 66 to 68, soft landing for imaging and testing of the lunar surface, that people didn't know what would happen if you landed a heavy object on the lunar surface until then. So the Surveyor program, although there were a couple of unsuccessful missions, but most of them were successful. And there's the machine itself on the Earth, obviously, but here it is on the moon, taking pictures, taking mosaic images in order to develop the detail that was necessary to begin analyzing lunar surface conditions. And this program basically developed soft landing capabilities. Now, the most important mission, in my opinion, was the Lunar Orbiter program, where we sent satellite around the moon, continuously snapping images, overlapping images. And it was, in fact, the lunar map that you see here that was published in 1971, it's a beautiful map. I put it up, you can take a look later. The base of that map, if you look through the geologic units, the colors, the base of that map is a photographic image of the moon taken by Lunar Orbiter. So the Lunar Orbiter data was essential in understanding lunar geology. Geologists pored over the images, and using the basic principle in geology known as superposition, developed in the 1600s by Steno, the superposition basically says, well, you know, if you have one crater that's resting on top of the other, well, that one's younger. You know, this is not a Nobel Prize winning concept, I guess, but over time, you develop this time stratigraphic framework or network that describes the sequence of events. And what we found was that through time, not only did cratering flux decrease, once we started with Apollo actually getting samples and getting numbers, but the numbers of, we found that the size of craters decreased with time asymptotically, with a huge flux at first, and then it's light cratering. It's a beautiful video coming showing that. But also the number of craters decreased with time. So it was the number of craters and the size of craters all decreased with time. And we started developing an image of what lunar geology was like. You can see the scan lines here, the Lunar Orbiter scanning and taking images. And the first Earthrise, of course, the Apollo 8 image, I'll show you that later, is the famous one. But this was actually the first image of the Earth from the moon, coming around the backside of the moon. And the images by Lunar Orbiter were quite spectacular. Here, the crater Tycho, which we now know is about 108 million years old. When dinosaurs were walking on the Earth, if they looked up at the right time, they would have seen this impact. It's got a wonderful central peak complex, which is an upthrust of material, kind of a relaxation from the compression related to the impact. And then the ground gets compressed, and then it pushes back up again. So that sends material out into a continuous and discontinuous ejecta blanket. And by mapping these blankets and seeing what craters overlap them and which ones are filled in by the ejecta, we developed a time stratigraphic image of the lunar surface development. This Tycho crater is kind of interesting too. If you notice, it has a terraced rim to it. These are slump blocks of material that fell into the crater after the impact along radial fractures that were related to the impact itself. So the whole study of craters and different types of craters and size of craters and huge basins. This one, the Oriental Basin, which is on the left-hand side of the moon. You can barely see it from Earth. Here it shows up because it's at the terminator in this particular image. And look at that huge multi-ring basin. And the multi-ring basin is actually caused by the compression of a huge impact, and the lunar surface actually developed a waveform that created this multi-ring. An enormous structure, hundreds of kilometers.
Can you give like a time scale? How long did that take to form, and the waves and how? And I guess it froze in place.
Oh, I almost instantaneous.
Yeah.
Yeah.
like a second.
Yeah, instantaneous. Yeah. The degradation of the crater, which is another useful indicator of age. You know, how the rounding of, you know, there's no atmosphere, there's no water, there's very little gravity, which slows things down. But still, there is degradation. You know, there is micrometeorite bombardment, there's cosmic radiation, no atmosphere. So there is an erosional aspect to lunar geology, and even that was studied to put things into a relative time perspective. But it wasn't until the Apollo missions that we actually got samples and were able to date those samples that we actually got numbers for the time scale. Before that, it was just like the terrestrial time scale, just based on superposition. Well, this is cuts across that. That's got to be younger, so that we'll put that in that system, and this system's down here, and that system's up there. That's the way you do it. Later on, you get the numbers by radiometric analysis. Saturn V. Again, I feel as though we eclipsed the Russians at this point with the development of Saturn V technology, all related to von Braun and his team. Curve weight, 6 million pounds, which was good because the engine thrust was 7 million pounds in order to get that thing off the ground. And you probably remember some of these launches. They were pretty spectacular. The Apollo 11 astronaut team, Armstrong, Collins, and Aldrin, they named a mineral after them. In fact, armalcolite is a titanium amphibole. No, it's titanium pyroxene that was found that has no terrestrial counterpart. And Collins, of course, stayed with the spacecraft while Armstrong and Aldrin took the LEM down and landed on the lunar surface. And even that was touch and go. There's a wonderful, wonderful video called Race to the Moon. And it's all about mission control. And Gene Kranz has a book as well, but they made it into a wonderful video. And they talk about what was going on during that landing. They were running out of fuel. They were running out of fuel. And then he was coming down for a landing. And it's only because these guys were test pilots and they were used to high stress environments. He was able to recognize what was going on and actually chose, with a small burn, a different landing site to land that thing. But they almost crashed on the lunar surface and ran out of fuel. It was very touch and go, seconds difference. So the Apollo 11 is just a couple of videos showing the rocket, and these have been publicized to a great extent. A tremendous achievement. And the Apollo program, of course, the Apollo 12 was struck by lightning as it took off, and that knocked systems out throughout the entire mission. And of course, the Apollo 13 mission, well, you know what happened with that one. Somebody put the wrong voltage heater into the oxygen tank, and it blew up when they blew the whole side of the spacecraft out. When that happened, and we were lucky to get those boys back. So here's the landing sites for the Apollo missions, Apollo 11, 12, 14, 15, 16, and 17. I would say 11 was more of a political statement, we beat you. 12 had some limited science, but the other missions were tremendous science missions. They were well planned out. They were sent to specific targets to learn about the geology of the Earth's moon. By the 1970s, the Soviets had landed 8 Luna missions on the lunar surface. The Apollos were 6 landings, of course, and the Surveyor missions in yellow also were around the lunar equator. Those were earlier, of course. Lunar origins, modern models suggest that the moon was born out of the Earth. Now, the composition of the moon, basically 2 rock types. One is a northocite, which is a very favorite stone used in Greek coffee shops. It's a kind of bluish, glittery material. It's all made out of calcium feldspar. A little bit of pyroxene in there, but mostly calcium feldspar. So that one of the earlier theories I remember, oh, the moon came out of the Adirondacks, because there's a lot of northocite in the Adirondacks, but no, the Adirondacks are not old enough. We know from our dating that the moon is actually about 4.5 billion years old, about the same age as the Earth. This is a bit of a incorrect image because it kind of shows an atmosphere around the Earth. At this time, the Earth had no atmosphere whatsoever. It was a large magma ocean, and a Mars-sized object impacted the Earth and sent, there's a computerized model up there showing what happened, a Mars-sized object hitting the Earth, getting incorporated into the Earth, and the residue orbiting the Earth and eventually collecting into the moon. These objects, much like the other planets, our vision, of course, is as gravitational collapse causes melting, and you wind up with an orb of molten material orbiting the Earth. So the moon starts out much the way the Earth starts out, as a large magma ocean with rock bergs floating at the surface of the moon because of the lower density of the crystallized feldspars. So there's two basic terrains on the lunar surface, forgetting about the cratering for a moment, try and take that visually away. But the mares are basalts, lavas, that float out onto the lunar surface. They're younger than the highlands. Notice they lap onto the highlands and in fact fill some large circular basins that were the result of massive impacts during a period of heavy meteorite bombardment. And we never knew this about our solar system until we studied lunar geology, that there was a period of intense large object collisions that affected the moon. I've got a nice video that shows that in a moment. In fact, I think it's coming up right now. Yeah, this is a beautiful video. I found it yesterday. Lunar reconnaissance orbiter. So here's the moon ejected out of the Earth from the impact. Huge magma ocean. Rockbergs start to form on the lunar surface made out of this rock I've been calling a northocite. And it gets hit about 4.3 billion years ago at the South Pole to produce the Aitken Basin. Enormous impact, the most enormous impact on the moon. In fact, antipodal to the impact site is a jumbled terrain that is a collection of the material that impacted themselves on the opposite side of the moon. And then basin formation is about 4.1 to 3.8 billion years ago. Massive impacts as the planets and their moons acted as gravitational carpet sweepers, cleaning up their orbits from the leftover debris of the initial development. Mare volcanism begins about 3.8 billion years ago and lasts to about 1 billion years ago. It's 2.8, almost 3 billion years of volcanism. And like dog pee on a sidewalk, the lavas stretched over tremendous parts of the lunar surface due to the lack of gravity and the lower viscosity of those magmas. Basaltic magmas, lavas rather, are very low in viscosity. So they flowed for great distances and filled in these basins. And then the last segment of lunar development is light cratering that took place in the last billion years of time, hitting both the mares as well as the lunar highlands. But the lunar highlands, the brighter areas of the moon, that's the northocitic material, that stuff really is busted up. It's totally broken. We have some wonderful pictures coming up showing those rocks in thin section view, so you can see what the damage was to what were formerly pristine minerals. So time. Geologists always do things from the bottom up, hence the term bottoms up, right? Older at the base here, there's two charts. So moon forms by Mars-sized impact, and northocitic lunar crust forms. The pre-Nectarian period then is intense cratering. It ends with intense cratering with about 30 multi-ring basins, including Procellarum and the South Polar Aitken basins. And then during the Nectarian, there's another phase of huge multi-ring basins in that couple of 100 million year time span, about I guess 200 million years, or is it 100 million? Anyway, and then the Imbrium and Oriental basins, of course, we've sampled that now. So that number is pretty firm at 3.8 billion years ago for the development of those basins. Again, starting at the bottom then, as we go upwards in time, the flooding during the Imbrium period, the flooding of the multi-ring basins eventually covers about 17% of the lunar near side, and impact cratering slows to about 1.5% of Nectarian rates. So that's the light cratering and the multi-rayed craters like Copernicus and Tycho, and the rest of them that are in the 100 million year category. There is, during the Eratosthenian, there are still some lavas that are coming out, but very great decrease in cratering. And then eventually the Copernican period, the most recent geologic period, the formation of rayed craters that have, and those rays degrade over time. That's why the youngest ones have these crater rays of ejecta that are shooting out, and the superposition of those crater rays with respect to other craters allows us to get a time stratigraphic image of what's going on the moon. Now, our current view of the moon is this. This is the left-hand side is the side that faces the Earth. And shown here diagrammatically is the fact that the lunar crust, and it has a crust, mantle, and a partially molten zone and a core with very deep moonquakes. We detected that with the seismographs that were left with the Apollo missions. But if you notice, the side that faces Earth, which is the side with the mares, has a thinner crust than the other side. And that's the multi-ring basin impacts are what penetrated through the crust and allowed magma to bubble up to the surface. Most of these are characterized by what used to be called mass cons, concentrations of mass that are probably remnants of the bolide impacts that took place during those periods. So just some boring data. You can look that up anywhere, as I did. And there's a nice view of some of the rayed craters, the most recent on the moon. And of course, here's the lunar near side spinning around, showing the large impacts that were filled with basaltic lava. So 4.6 billion years. There are some gases in the atmosphere, but the atmosphere is practically non-existent. No magnetic field, and it has about a 16% of the Earth's gravity. And that's one of the reasons why the lava's flowed so far, because of the lack of gravity on the lunar surface. Here's a view of the Aitken Basin at the South Pole. This is a Clementine image. The Clementine missions were in the 1990s, I believe, and they detected water ice, quite a bit of it, in fact, in the South Pole. So in terms of target for inhabitation, that's going to be it, South Pole of the moon. Remember, you heard it here first. Here's an image of the lunar far side, a beautiful picture of a central peak complex. That's the upthrust material that comes up. It's filled by mare material with light cratering and a kind of a degraded terraced rim. Two younger craters that you can see in the foreground there, one hitting the other, and the smaller one is younger than the bigger one.
Again, when this formed, how long did it take? Just a few seconds for the shape to...
Oh yeah, it's instantaneous. Yeah. The only thing that takes some time, and again, there's no atmosphere, so things can travel greater distances and the low gravity. So any ejecta that's blown out will take a while to settle down. All that structure is instantaneous. Yeah. Here's the crater Copernicus. on the, and that's about 800 to 900 million years ago. And you can see it's puncturing through the basaltic lava of the mares. A lot of these pits that you see in the lower right-hand area, some of them are craters, but some of them are volcanic vents. So we have detected not only flow front features of lavas, wrinkle ridges and the like. There's a picture coming up, you'll see those, particularly where the lavas float up against the edge of a crater. You start to see this kind of wrinkling of the top of the lava flow. It's kind of similar to what we see on Earth. Beautiful image of Copernicus. Here's another more oblique view of Copernican crater. You know, I can't remember. That one's probably half mile, something like that. I would think something like that. Yeah. With the growth of technology, we sent the Galileo mission out to Jupiter, of course, but the Galileo mission used the moon, it whipped around the moon twice or three times, and then slingshot out to Jupiter. So gravity assist method has been used for quite a long time. It had the instrumentation to take this image showing in blue the high titanium lavas and in red the lunar highlands, the North Acidic material that is the more ancient lunar crust. So as technology increases, you know, we get better and better imagery of the lunar surface. Here's the Clementine that made a topographic map of the entire lunar surface. So you can see some of the basins are 8 kilometers, sorry, some of the highest points are 8 kilometers high, and some of the deepest parts are getting on to 4 to 8 kilometers deep. So that's about, you know, 6 miles or so, 5, 6 miles, something like that is the deepest part. There's the Aitken Basin, 12 kilometers deep for the Aitken Basin, largest impact feature in the solar system. And as I said, the Lunar Prospector found water ice, and other missions now have verified that that water ice at the South Pole. Okay, the petrographic microscope, it's one of the tools that geologists use to confuse the layman and give us a sense of self-importance. But the petrographic microscope enables you to really get down to the nitty-gritty of looking at minerals under polarized light. Minerals are like small little prisms, and you have two different polarizing materials at 90 degrees to one another. So when there's nothing, when there's no slide there, it's black. You know, one vibration direction cuts out the other one. But when there's a mineral there, the lattice and the ions in the minerals distort the light, so you generate colors. And you can actually identify minerals using their interference colors. But more importantly, I use petrographic scope all the time because it tells you everything about the rock's history. The textures in particular are very, very telling. So let's take a look at the plutonic and North Acidic rocks, the oldest rocks on the moon. Here's a block of ejecta that was blown out, and you can see the size of the thing. The Apollo 16 and 17 missions sampled the oldest sections of the moon. This is a North Acidic rock. PG stands for plagioclase. It's a high calcium plagioclase, high temperature. But the thing that's distinctive about it is the fracturing. The fracturing is pervasive. On Earth, anorthosites are beautiful big crystals, kind of like that big feldspar with the black and white twin striae. That's a typical terrestrial texture, igneous texture. But on the moon, the anorthosites look like this. They've been hammered. Continuous cratering for billions of years, shock metamorphism, creating cataclastic textures in the rocks. Here's another one. Those are twin planes, the black lines that are continuous. Those are twin planes in the plage, very distinctive for that particular species. But the fracturing is unusual. Here's a norite. A norite is an orthopyroxene bearing gabbro. And this is in plain polarized light. In polarized light, it looks like this. That's OPX, stands for orthopyroxene. It's an orthorhombic pyroxene, high temperature. And the plagioclase, everything's all busted up though. Here's another norite that's shocked. Orthopyroxene, impactite glass. Glass that's related to instantaneous high pressure, high temperature impacts, melting the silicate into silicate glass. You just don't see that on Earth. Now the basalts, there are porphyritic basalts similar to terrestrial basalts. There are olivine basalts, rich in the mineral olivine. But some of the unusual basalts on the Apollo 17 were the high titanium basalts. Here's a view of the lunar mares, and at the top part of this image, you can see the wrinkle ridges and some of these more oblong craters. Well, they're not low angle impacts, they're vents, they're volcanic vents. And the kind of linear feature that you see snaking across from that side to that side, that's a lava tube, collapsed lava tube. Kind of similar to the features that we see on the Earth also. So the volcanic origin of the mares is clear. And the basalts, they look like this. Beautiful crystals of plagioclase, PG, and clinopyroxene, similar to terrestrial basalts. Porphyritic basalts are that's plain polarized, that's cross polars. Clinopyroxene, plagioclase rocks. Notice that the clinopyroxenes are larger than the other crystals. Everything's busted up and broken, but try and eliminate that from your view and just recognize that the clinopyroxenes are much larger than the other crystals. Well, that's what we mean by a porphyritic texture. Porphyritic texture is a two-stage cooling history where large crystals form at depth, and then the magma, along with those early formed crystals, erupt onto the surface. We get similar textures in terrestrial rocks also, which is why we recognize them. Here's another porphyritic basalt, cross polars showing the clinopyroxenes and the ground mass that's made of all busted up plagioclase. Olivine basalts, these are beautiful. This is plain polarized light, and in cross polars, high magnesian olivine, the phosphoritic olivine, high temperature, high pressure phases. Not found in too many places on Earth, high magnesian olivine basalts in a matrix of plagioclase. And here's another high titanium basalt. Black in this plain polarized view are opaque minerals, probably ilmenite, which is a titanium-rich phase. And it grows in equant crystals as well as long linear crystals. In fact, some of those more equant-looking crystals are probably perpendicular to the stage, so they're kind of similar in shape to the more linear shapes. And that's what that looks like, mostly clinopyroxene, some plagioclase. Now, the lunar breccias and soils, the Frau Moro Formation was sampled by Apollo 14, and the Frau Moro is a fragmental rock. It contains beads of glass, brown glass. Some of these are aerodynamically formed. They were blown into the non-atmosphere and then dropped back onto the lunar mares. There's a plagioclase crystal up there with beautiful twin striae and lots of opaque minerals in there as well. But the glass beads are rather interesting and a very important component of the lunar regolith or soil. And here's a polymic breccia where you actually have the impact of lunar mare material that then creates a clast of basalt swimming in fine-grained matrix of highly comminuted rock debris and large plagioclase crystals broken up as well. There's another polymic breccia. So these are very, very distinctive rocks, lunar rocks. Well, say thanks for attending. I appreciate your interest in this rather interesting topic.
right, that is Mark.
Thank you.
Thank you. Do we have any questions?
Can you speak about the early tidal dynamic when the proximity was different and what effect that had on the lunar development?
Well, there's no question that the moon was closer to the Earth. It's been moving away. Right now, it's in a total gravitational lock. But I'm not sure. I mean, I'm just thinking out loud, right? The tidal forces, the Earth being larger than the moon, it would definitely create an asymmetry, and that perhaps is the reason for the difference in thickness. I think the crust is 75 kilometers on one side, the near side to the Earth. The other side's 150 kilometers. So there's a big difference in that. And, maybe that's part of the reason for the tidal friction. Oh, sure. I mean, I'm just talking off the top of my head. Yes, Willie.
If you were allowed to choose, where would you send the next mission to the moon?
Well, it depends if it's manned or not. If the intention is to set up a permanent station, then I'd bring some nuclear stuff up there to keep things going and set up camp down at the South Aitken Basin. Absolutely. Because there'll be water.
What if you were just sending a robot and you wanted samples?
Well, we did that already.
Well, is there any place you would like to go that we haven't gone to?
No place in particular. I remember telling my ex-wife once, I was lecturing just like this on lunar geology, and came home that night, and the moon was out beautiful. I said, Miriam, I said, look at the moon. I said, isn't it beautiful? I said, wouldn't you want to go there? And she looked at me like I was crazy and said, why would you want to go there? You go there when you die anyway. I said, okay. That's why.
Yeah, 1 second.
Sure. So I have no preference to answer your question. Any place would be good.
Right, 2 questions.
Okay.
I apologize in advance for both of them. What's your favorite crater?
My favorite crater? Yeah. I like Tsiolkovsky.
Why is that?
Because of Tsiolkovsky.
Okay. Good answer. And then
I like the name,
I promised a friend I would ask this.
Okay.
So I'll deny culpability.
Okay.
Do we know what the moon smells like?
What does it smell like?
Yeah. You do.
I have no idea. Oh, really? Oh, interesting.
Okay.
Yeah. Huh. Any questions on Zoom? Nope. Okay. Anyone else in the, whoops. Let's see.
Why are there no water oceans on the moon, but on Earth we have them?
The main reason is the size of the moon. It's just not big enough. And also its origin. Lack of gravity, any liquid water on the moon, gone. They're just dissipated in space.
Hello, could I ask a question?
Oh, sure, go ahead.
Hi, I'm on Zoom. I was wondering about this idea of mining on the moon. Like countries are talking about mining stuff on the moon, and it seems to me like we wouldn't want to take anything off of the moon. Keep the balance. Don't mess with the balance at all. Is that like not a good idea?
I don't think. Well, the main problem with mining is getting the stuff back here.
Well,
but
they talk
any form of mining is not going to change the dynamics of lunar rotation or.
Okay. Why wouldn't it change it? If you took, say, 25% of the mass away, wouldn't that have some kind of effect?
Well, mining 25% of the mass of the moon would be a hell of an undertaking. I'll tell you that.
Well, they do that.
Moon is a harsh mistress by Heinlein.
Yeah, no.
Okay, so I don't got to worry about it then.
No, don't worry about it. There's plenty of other things to worry about.
Okay, thank you. It was a great presentation. Appreciate
You
it.
bet. Thank you.
Do you have any idea of why there's so many of the huge impact basins on the near side of the moon?
It's an interesting point. I don't know I don't know if anyone has come up with an explanation for it, but the thing that people always hide behind is the fact that the moon, same side, faces the Earth. So these could be impacts related to the first fission of the moon away from the Earth, and the leftover debris just kind of sucked in. I don't know. We do know from our study of all of the other, particularly the planetary moons, that this period of intense meteoritic bombardment between 4.3 and 3.8 billion years ago, it's as if somebody shut a valve over 3.8, as all these larger bodies got sucked into the evolving planets. So we see that footprint on every body that we've studied in the solar system. You know, that aren't gaseous and frozen. And even then, you know, of course, a lot of those surfaces are rejuvenated, but any older surfaces show intense cratering. Don't know.
Further questions in the room? Any further questions on Zoom? Okay. Well, thank you so much.
My pleasure.
Lovely. I was supposed to improve things, not do that.
Oh, say there are a number of planetary articles on DukeLabs.com website, but most of my work has been in tunnel geology and just terrestrial geology, in particular New York City geology. So you'll find quite a bit of, you might say, pollution under the publications tab of the DukeLabs website.
All right, thank you so much. That was wonderful. Let's see, Jim, if you're still out there, I think we ended up with about 25 people in the room. We collected quite a few after things started. That was marvelous. Always been one of my favorite subjects, that's for sure. With that, we will close the September meeting of MHAA. For the folks who came in after we started, generally after the meeting, several of us go down to Pasquale's Pizza. It's down 299 across from Tops Plaza, and sit there, chat about things we didn't get to here, have a slice of pizza or something, or a cup of coffee. I think they have coffee. And just hang out for a bit. Also hang out around here for just a little tiny bit, cleaning up, getting everything set up. So thank you all for joining. Lots of extra
Jack,
folks.
sorry.
Oh, yes, sir.
I know the kids, whenever I lecture, get a charge out of this, but there's a piece of the moon in this box.
Oh, yes.
If anybody wants to see it, just come up. Betty's in charge.
And from the earlier question, I did sniff it.